Hi, this is Shashank Singh Kumar from Georgia Tech, and this video is my lab report for the motion of a falling object. The lab is based on the comparison of an object falling in real time and a computation model with gravity and no drag and with gravity and drag. These are the sections that I will be covering in the lab. Significant concepts include Newton's second law, which is a significant idea expressed by the following formula: F net is equal to delta P by delta T. This is a case where net force is not zero and points downwards as the object falls downwards, causing an acceleration. The forces acting on the cloth are the force of gravity and drag. The following are formulas of significance listed below. The system consists of the cloth falling and the air which causes the drag. The surroundings consist of the earth pulling the cloth towards it. The following is the free body diagram, where the drag force points upwards and the gravitational force points downwards. Drag force is proportional to the square of velocity, hence as the cloth falls and its velocity increases due to acceleration due to gravity, it will also increase the drag force. As the drag force increases, it becomes closer to the gravitational force, the cloth will get closer to a terminal velocity. The purpose of the experiment is to measure and compare the motion of a falling object in real time and a computational model of the same with and without considering drag. This will help us understand the numerous forces acting on the cloth and how they affect the motion of the cloth. The brief conclusion of the experiment is that the computational model for gravity and drag is extremely accurate when compared to the real observed motion. The following video is the analysis of the motion of the tied cloth falling downwards in tracker. The mass of the shirt is 0.130 kgs. The motion lasts for 0.433 seconds. The cloth is dropped a length of 1 meters and the motion starts from the vector 0, 0, 0 meters. The following is the coding for the first computational model of only gravity and no drag. The following are the system properties and initial conditions. The ball mass has been entered in line 36. Delta T has been set at 1 by 60 in accordance to the frame rate of the camera used in line 44. G has been given the value of 9.8 in line 49. J hat has been changed such that it only exists within the y-axis in line 52. The following is the calculation loop. The time span has been set as 0.433 seconds in line 65. W, being the vector for weight, is calculated by multiplying the mass by G and J hat in line 70. W is the F net as drag is ignored. The velocity update formula from slide 3 is used in line 75. The position update formula from slide 3 is used in line 77. The following is the code for the second computational model, which includes gravity and drag, system properties and initial conditions. The only change in the formula with regards to the previous formula for the system properties and initial conditions of the coding for only gravity is the fact that there is a B over here, as the proportionality constant being given the value of 0.025 through trial and error. The calculation loop. The only difference with respect to the first computational code over here is the addition of Fd, which is the calculation of the drag force. W is added to Fd, giving us F net. This is because drag is not ignored. The following are the graphs resulting from the code. For gravity and drag, acceleration in the minus y direction is non-constant, hence not a straight line for velocity versus time. Whereas for only gravity, acceleration in the minus y direction is constant, hence a straight line for velocity versus time. The position versus time graphs form a similar curved slope for both. But the distance traveled in meters by the gravity and drag graph is almost half of that of the only gravity graph. Comparison of the predicted graphs and the observed graph. Real-time motion versus computational motion with gravity only and gravity and drag. The real-time experiment and computational model for gravity and drag produced very similar results due to the consideration of all major forces in the computational model and accuracy of the experiment. The graph with the computational model with only gravity is much more inaccurate and displays much greater change in position because the drag force in the opposite direction is not accounted for. However, there are possible discrepancies within the charts which will be discussed in further detail in the next slide. Errors and assumptions leading to differences between computational models and real-time experiment. There may have been errors as some points on tracker were entered by hand, human error. The cloth may not have fallen in an absolutely straight line in relation to the camera, human error. It is difficult to measure the center of the cloth as it does not form a uniform shape, systematic error. Discussion questions. What does it mean? Which models predict terminal velocity? Only the computational model, which includes the calculations for the force of gravity and drag force, will predict terminal velocity. This is because if there is no drag force, then there will always be a net force pointing downwards, causing a constant acceleration. However, the presence of a drag force which increases the velocity results in the forces cancelling out and thus being able to produce a net force equivalent to zero. Thus, in accordance to Newton's first law, causing a constant terminal velocity as there is no net force on the object. What if? What is the effect of initial velocity on terminal velocity? The initial velocity has no impact on the value of the terminal velocity of an object, as terminal velocity only depends on the surface area of the falling object. The time taken for drag force to become equivalent to the force of gravity changes, and it takes longer for an object thrown downwards to achieve terminal velocity when compared to an object dropped from rest. As seen by the graph obtained from the changes in the code, the position at t is equal to 0.433 seconds is minus 2.15 meters, whereas when initial velocity was 0, it was minus 0.9 meters, which is much closer to achieving terminal velocity. The changes in the code displayed and the corresponding graph produced prove the same. Thank you for listening, and I hope this presentation was useful.